Hello and welcome. This is Aaron again. Welcome back to Wednesday's recitation from the week of March 10th. So we're going to be doing the second problem today, or right now. So in this one we have two dogs, one room, and the other quanta is much smaller than room. These are real dogs too. If you've seen them, they are quite disproportionate in size. Anyway, we have room pulling quanta on a sled up a hill. And we're going to try to figure out like the steepest hill they can go, given the friction coefficients between room and the hill, and also quanta's sled in the hill. So let's start off by drawing a picture of our hill. So we'll do that in blue. So we can draw a line like this, another line like this, and then we have, so we'll call this angle here theta. Okay, so this is our hill. So if we zoom in here, let's see, let's take a look. Let's draw these dogs on the hill, do it in purple. So we have a dog here, this is room, bigger dog. He's gonna be pulling, he's got like a collar, pulling up a sled, which we'll just draw like this. And then we have a little dog, room, we'll do room, or quanta in green. Okay, so we do this, we do a little dog, doop, doop, doop. And he's like sitting, or yeah. Okay, so and she quanta is sitting. Okay, so we have our picture. So and they are moving in this direction. So first thing to do is think about our coordinate system. So this is one of those problems where a tilted coordinate system is going to be our best bet, because then our normal forces and our direction of motion will be in one dimension. I just dropped my AirPod on the floor. I wonder if you heard that. Anyway, so let's do that. Let's just draw a coordinate system really quickly. So we have our coordinate system. So this is y and this is x. Okay, great. So now let's draw force diagrams for these dogs. We'll start with room. So draw room like this. Do a little circle. So room's obviously got gravity. Fg. Write its vectors again, like in the last problem. And then we have the normal force from the ledge, from the slope. Okay. And we have a tension force pulling, which is going to go this way, which is going to be the tension force from the rope, which is pulling quanta. And we also have friction, but we got to think carefully about friction. So room is going to try to push up, which means he's going to like push his paws into the surface and hope that they don't slip, and that they will and that he will get a friction force pushing back on him, which will push him up the hill. So friction actually pushes this way, and it's static friction. So we'll write that as friction. Let's put a little s there to remember, or we'll do a little f, s to remember that's static friction. Now for quanta, draw quanta over here. So quanta's over here. Quanta's also got gravity. Oh, that's my eraser. Tap, tap. Beautiful. So quanta's got gravity also. And its tension points in the opposite direction of room's tension. It's pulling quanta up, so that's great. And it's got normal force, and it's got friction. And this time friction is going to push down because it's sliding, the sled's sliding, and it's got some coefficient of kinetic friction, which is resisting the motion. So it's going to point this way. So we can write force, tap, tap, force, friction, kinetic. Okay, so that's great. So now we can write out now we can write out our equations of motion. So we can assume that, where does it say anything about the speed? Constant speed, yes. So yes, an angle theta at a constant speed. So what does constant speed mean? Constant speed means the speed is not changing. So if the speed is not changing, what does that mean about acceleration? It means the acceleration is also not changing, or acceleration is 0. So we can write that in on the right-hand side of Newton's laws. So we just have the left-hand side of Newton's laws to worry about. So let's write out our two equations for room in terms of vectors. So let's do that like this. So we can go back to pencil, room. Yeah, we'll rewrite that. Okay, so room's got force friction, or so it's got friction. And we'll put these into vectors now. So let's translate these back into vectors. So we got the force of friction, which is only in the x direction, and it's in the minus x direction, and it's proportional to the kinetic coefficient, room conserved force, mu static Fn. Yep, this is the static force of friction, I mean. So we'll write that in here. Us Fn. Beautiful, it's proportional to the normal force. So that's great, and it's got 0 here. And that's the force of friction. Oh, and it's minus because we're pushing the, it's going in the minus x direction. Plus, then we've got the normal force. The normal force is only in the y direction, and it's in the positive y direction. We just write it just like this. That's great. And then the tension force, which is only in the x direction, but it's positive, so we'll write it like this. Tension, 0. And force of gravity. So this one's a little bit trickier because it's in the x and the y direction, because it's going to have component goes like this. You can have a component like this. So it's x component, and we can deduce theta here by, we can think about it. So like this angle is theta, which means this axis tilted away from its original position by theta, which means this angle is theta. Okay, so the x is going to give us, just like the past problem, it's going to give us sine theta. So we're going to get mg, we'll write it outside, mg cos theta, or sorry, sine theta. And then the y direction is going to be a minus cos theta. And this is equal to ma, but a is 0, so 0. And this gives us two equations. So we have the top one, the x equation, and the y equation. So let's write this out for quanta. And let's write out the equations for quanta. So let's do that. Quanta. Okay, so quanta's got, oh, this was, I guess what do we call it? We gotta be careful about our masses here. So this is m room's mass. Okay, we'll write that like that. And then we have, so this is going to point in the positive, the force of friction is going to point in the positive direction. And, oh, this is Fn. We'll go to a little comma, and this is room's normal force. The same thing there. So this is going to be mu k Fn quanta, because it's going to point in the positive x direction. And then we have the normal force. So we'll write this as 0 Fn q. The tension force is going to be a minus sign, so we point backwards. The tension on one is equal to the tension on the other, plus m quanta g. And again, same situation with the force of gravity as before. We just write that in. Sine theta minus cos theta equals 0. Okay, awesome. So now we have 4 equations. So we can start plugging in things we know. So we already kind of did that, but we can solve for Fn with the second equation. So we can solve for this by moving this term, mrg cos theta, to the other side and get fnr. So we can solve that immediately. So we can go back here, we write fn room, physical meaning of quantas, physical meaning of each term, i.e. component of quanta's weight parallel to the rope. Yes, so I think I went through that. So I'm just going to write in, I'm going to start to solve this right now and work on solving this equation, or solving this system of equations. So we just found Fn for room, which is equal to m room g cos theta, and Fn for quanta is equal to m quanta, write that lower, g cos theta. Okay, so now we have we can plug these values into our top equations. So we can do like this. We can go whoop, whoop. We plug into our top equation. So we're going to plug into here, here, and then write out these top equations. Okay, so let's do that. Let's plug in. So we have minus mu s Fn room, so m room g cos theta plus tension plus m room g sine theta is equal to 0. Okay, so we can, that's good, so that's good. And then we can plug into the bottom equation, and we get, let's do this, and we'll write mu k. All right, solving for the bottom one, we found Fnq is equal to mg cos mqg, so that's good. Mu k mq g cos theta minus tension plus mq g sine theta is equal to 0 also. Okay, so one thing we can do, so we have two equations, and the only things we don't know tension. I'm going to use my laser pointer. We don't know tension, and we don't know theta. But let's see here. We can find an expression in terms of that just has theta if we add these two equations together. So if we add this equation to this equation, they're both equal to 0, so we can do that. The t's are going to cancel. So let's go ahead and do that. Another way to do this is to solve this equation for t and then plug that value back into here. But I like the idea, I like summing these equations, because then we're going to have some common factors here, like this g cos theta and this g sine theta, which we can pull out. So let's do that. So if we sum these two equations, we can call this, they'll be equal to 0, so we'll set equal to 0. So we'll say 0 is equal to, and if we pull g cos theta out of these first two, so we'll get g cos theta, we get a mu k from the bottom part, mq minus mu s mr. T's canceled, that's great. And then we add these two parts together, we can pull out another g sine theta plus g sine theta mr plus mq. Okay, so now that we have this, well, the g's are going to cancel, so we can erase these g's. We can divide through by g, and that's fine. G is not 0. So then we have these two things. So then we can write, we can move this term over to the other side, which just means we could erase this right here and add a minus sign to it and make this an equality sign. Okay, so that's good. And then why not just bring this minus sign inside of this expression, bring this minus sign in here, and then rearrange these terms. So I'm just going to erase this, do some erasing. So this was mu s mr minus mu k mq, just so I remember. Okay, back to here, mu s m. If you ever forget, the static one was room minus mu k m quanta. Okay, so then we can divide sine by cosine and mr this thing by this, and we get something that's sine over cosine is tangent. So then this is going to give us, running out of room here, tan theta is equal to, what do we have? We have mu s m r minus mu k m q. Oh, really running out of room here. Okay, over m r plus m q. And with this, you can find theta as the arctangent of this. And we know all these things because they were given to us. So we can plug this into our calculator and find theta, and we can solve for theta, and this is going to be the maximum theta that we have traction, that room still has traction, because room had just static friction, we assumed. So that is pretty much the answer. So I will stop there.